One of the big things as we elevate our level of knowledge in science is that we look at two different components, accuracy and precision. And precision is things that we know for certain. And so, for example, when we did the Metric Olympics and we did the water squeeze where we squeezed water into a 1 liter beaker, and then from there you poured it into a 100 milliliter graduated cylinder, we saw that on the beaker it looked like it was 100 mils, and yet when we moved it into the graduated cylinder, which had more increments, that it was actually 91 or 95 milliliters. And so when we are looking at what we know for certain, those come with the values that we write down in an answer. And so significant digits always are what we know for certain plus one more spot because we're making an educated guess. Leading zeros are not significant digits. And so when we look at an example of we typically don't write our numbers this way. When we're talking about 190, we write a number like this. But when we're talking about something behind a decimal, we know a couple things about this. We know that this is the 10th, 100th, thousandths, 10,000ths, and 100,000th spots. And we know that these places are important because when we look at, for example, the Olympics are on right now, and we know that the difference between gold and silver can be 1,000th of a second. When we look at this particular number, however, there are not 5 significant digits here. One would like to think so because this is a decimal and these are all placeholders. We know that this 2 is in the 1,000th spot. This is in the 10,000th spot. This is in the 100,000th spot. However, there are actually only 3 significant digits in this answer. These zeros here are what we call leading zeros. And they don't count in our significant digits, simply for the fact that we can rewrite this number as 2.74 times 10 to the negative 3. And now these 2 zeros out here are no longer required for a placeholder. This situation here, if we take 2.74 and we divide it by 1,000, we would get this value. Now, if I was to write this number, this is very important here. There is a big difference in the precision between 5.97 and 5.97000. This could be the difference between, like if we were looking at this, this could be, let's say people, 60,000 people. This one here is 59,000. 597,000. Sorry, I need one more zero. This is 600,000 people. This is 597,000 people. If you were to cater this event, there is a big difference between these two values. 3,000 people is a significant value in your budget. And so trailing zeros do tell us quite a significant amount of information, and so they do count as significant digits. And we're only going to round the answer to the correct significant digit when the entire problem is solved. So for example, if you're doing some math and you look through, and this is the answer that I get here, 23.611111111 repeating. If I was to round this number and then take it into another question and keep going, my value is going to change. Always, 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 until you're ready to put an answer down saying, I have completely solved the problem, always keep all of the digits in your calculator. And you don't need to write down this number on a piece of paper. Your calculator, if you're using a TI-83 or a TI-84, you are able to go using your up and down keys to pull out a number and use it without having to type all those numbers in again. Because the minute that we start writing things down from our calculator and then trying to put them back into our calculator, we can create a transposition error, and you don't want that. So always make sure that you can use your calculator to pull out the numbers, and then you could solve it. Okay, significant digits is your very last step in completing a calculation. All right, so this is going to go way, 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 way back. Out of all the numbers being added or subtracted, the number that has the least amount of decimal places, which means the least precision, determines the number of decimal places in your answer. And when adding or subtracting, you're just going to be limited by that. So if I was to have 190.56 plus 23.8652, my calculated value is 2, 5, 12, 14, 4, 11. 214.4252. We are, however, limited by that level of precision. We can only have to the hundredth spot. So our answer that we would record would be, here's the 2 decimal spots. So this 5 is going to have an influence on that too. And we only ever look at one number past where we're going to write our answer. So our answer would be 214.53, and that's what we would record. The same is true with subtraction. And so we have 1, 3, 8. Oh, I can do that one. 2, that was 9. 7, 6. Okay, I feel like I need to double check this. 190.5639 minus. Yes. Okay. Every now and then, doubt myself. Again, we're limited to the precision of this answer. We can only be as accurate as this value is. And so because it's 2 decimals, this 3 is going to have a play on the 8. I get 167.28. So anything, if it's a 5, it's 4 and down, we don't round. And 5 and up, we round up. And actually, the industry standard with regards to 5 is however you do it, as long as you consistently do it that way. So if you've always learned in your world to have 5 and down be rounded down and 6 and up be rounded up, then that's what you do, as long as you consistently round the same way all the time in your reporting, in your calculations, any piece where you're writing a number down. Okay, multiplication and division, it goes by the total amount of significant digits in your question. So if I have 23.4 multiplied by 4.56, I'm going to cheat. I'm going to use my calculator. We get 106.704, except, well, they're both 3. 1, 2, 3. This one is 1, 2, 3. So I'm going to start on my forwardmost digit that works, 1, 2, 3, and my 7 will have a play on the 6. Therefore, my answer will be 107. If I have a problem like this, 23 divided by 492. I'm going to cheat, use my calculator. 23 divided by 492. My answer is 0.0467479675. I am limited by this 2 digits. And so again, I'm going to start with the leftmost value, which is this one here, the number 4, because leading zeros don't play a factor into it. This 7 is going to have an influence on the 6, and so my answer is going to be 0.047. But what happens if I get a number like this? 235 multiplied by, pick a number, multiplied by 16. 235 multiplied by 16 gives me 3760. I'm limited by this number here, 2 significant digits. There's 2 here, there's 3 in this number. So starting, this rule is always the same. You always start on the farmost left. Here's my 2 significant digits that I'm dealing with. That 6 is going to have a play on it. But what happens is 3,800 is not 2 significant digits. It is 4 significant digits because these 2 zeros are important in our level of precision. What we need to do then, and we're going to talk about on the next page, is we need to change it into scientific notation. And every time, if this is our invisible decimal here, every time we move this decimal to the left until we have a whole number, a decimal, and then our value, this is multiplying or dividing by a factor of 10, by a factor of 10. 10, 100, 1,000. I'm going to multiply this by 10 to the power of 3. Okay, we'll explain this more, but just so you know, now I've satisfied my 2 significant digit rule. When we're looking at exact numbers, they are what they are and we don't change them. There is a big difference between 800 people and 8.0. We can't get a point of a person. It doesn't exist. Either you're alive or you're dead. You don't get a point of a person. So these are what we call exact numbers, and we don't change them. No matter what's going on for our numbers of significant digits, 800 people is 800 people. When we're looking at a ruler, these markings tell us levels of precision. This for sure is 1, this for sure is 2, this for sure is 3 units. Within this, we have the ability to make educated guesses. With confidence, we can say that that's 3.5. With confidence, we could divide this into 4 sections and say that's 2.25, 2, 2.5, 2.75. So if we said 2.25, it would be 2.3, and 2.75 would be 2.8. Or we could divide this into 0.2s. 3.2, 3.4, 3.6, 3.8. We can say our number, this front number, absolutely. And the second number we can say with confidence. When we look at this type of ruler, the markings are put in there for us already. So we know for sure that this is 7.2. We can look in here and we can with confidence say 7.15, 7.10, or we could say 7.25, right here, this number here. 7.2 with accuracy, and then we can with confidence say 0.25. So it just depends on the gradings, and that's why when we did the mini metrics and we had a beaker that had 100 mil marking, 2, 3, 4, 5, 6, 7, all the way up to 1,000, and we had fluid in here, and everybody's like, oh, I squeezed out 100 milliliters. And then we took that beaker and we put it into a graduated cylinder. And inside that graduated cylinder, there were finer markings. And we were able to say, oh, you know what? That's actually only 91 milliliters because of the level of precision for the containers. All right, scientific notation. This is where we live, okay? And so we need to get very, very comfortable with seeing it on the paper, putting our answers on the paper, and seeing it on our calculator. So if I was looking at this value here, I can't even begin to guess. This is 1,000. This is 1,000,000. This is 1,000,000,000. So 5,236,978,000 kilometers needs to be recorded to 3 significant digits. So when we're looking at scientific notation, we always need a whole number, then the decimal, and then however many decimal places to satisfy our significant digits. So if I was looking at this, it said 3 significant digits. I would be looking at 1, 2, 3. Those are the first 3. We always start from the whole number. So we would say 5.23. This satisfies our 3 significant digits. And then we need to remember that as we move this decimal into this position, it's a factor of 10. 10, 100,000, 10,000, 100,000, million, 10 million, 100 million, billion. I didn't count my jumps. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, on our calculator, 5, 2, 3, 6, 9, 7, 8, 0. Oops. 0. Sometimes it will give you an answer. Let's just see. Let's go that times 3 times 10 to the 8, or 10. So you can see on my calculator here, I took this really big number, 5.23 times 10 to the 9, and I multiplied it by 3 times 10 to the 10, and I got 1.5710934 e 19. On a TI-83 or a TI-84, this notation is times 10 to the power of something, some value. That's what E means, times 10. When we're entering it into our calculator, say I want to calculate frequency, and so the speed of light is 3, so I'll just write something down here, and I want to find frequency. Speed of light is 3 times 10 to the power of 8, and the wavelength is 7.5 times 10 to the negative 9 meters. This is meters per second. Well, first I have to rearrange my equation, so it's going to be V over lambda is equal to F. And so when I do this, a lot of you like to do this. 3 times 10 to the power of 8. Every keystroke you do in your calculator is an opportunity for error. And so you are going to elevate your level of math. You are going to start using this button right here, where it says here's the 7, here's the comma, here's this EE button right here. You will now go 3 second EE. On our calculator it says EE, but on the display it will show 1E. And then you will put in your 8, because that E is the same as this times 10. Okay, it does the same thing. So then I'm going to divide it by 7.5 times 10. So I'm going to use my E button, the negative 9. And I'm going to get 4 times 10 to the 16 hertz. Now, when I look back at my problem, 3 has one significant digit, 7.5 has two significant digits. So therefore, my answer is limited by this one significant digit. I can only have one significant digit in my answer. Okay, so I really want you to extend. I can do this. I can go 3 times 10 to the power of 8. And then I gotta go space. Divided by 7.5 times 10 to the power of negative 9. And go enter. And see, I get a completely different answer, because this is what's happening. My calculator is going 3 times 10 to the power of 8 divided by 7.5 multiplied by 10 to the negative 9, instead of 3 times 10 to the power of 8 delete, divided by Do you see how many extra keystrokes that was? Get in the habit of 3 times 10 to the power of 8 divided by 7.5 times 10 to the power of negative 9. I don't need brackets. I don't need all those extra keystrokes. I don't need to make sure that my calculator is doing the math the way that I want it to do the math. Make sure you're using these E buttons. It's very, very important. But you're going to pause here. You're going to go and you're going to try these calculations on your own. Now we're going to look at unit analysis and conversion. We move quite a bit. When we are talking about base units, I'm just going to use this to draw a line in here. When we talk about base units, there's some for physics and there's some for chem. They're identical, we just use different ones. We use kilograms in physics and we use grams in chemistry. We use liters in physics, we use liters in chemistry. We use meters in physics. We don't really worry about meters in chemistry, and we use seconds in physics, and we can use time in chemistry. But this is the big one, is the grams versus the kilograms. And quite often you will see milligrams and milliliters in chemistry. Here we could see megaliters, or we could see millimeters in physics. We could see milliseconds. Okay? We need to know how to get everything back to our base units. And that's right here. Base units is times 10 to the power of 0. So you can see 10 to the negative 1, 10 to the negative 2, 10 to the negative 3. What's happening is this is decreasing by a factor of 10. By a factor of 10. I should write divide here. If we look at this jump here, negative 3 to negative 6, it's by a factor of 1,000. This one here is also by a factor of 1,000. This one here on your sheet, this catches a lot of people up. Because this 10 to the power of 0 is not on there, this jump right here, 10 to the negative 1, and then you got to go 10 to 0, and then 10 to the power of 1, is actually a jump of 100. So make sure if you're relying on this chart, you're paying attention to what's going on here. You need a 0 in here, and that would be 10, and then that would be 10. This is increasing by 10. This is increasing by 10. Pay attention here. We're going from 3 to 6. We're increasing by 1,000. And again, we're increasing by 1,000. And so if you're looking at a unit and you see something like this, you're like, man, I have no idea what that is. Well, we know that this part of the unit is meters. And then we look on this chart and we find this symbol right here and we see micro. This is micrometers. Okay. How do we move up and down this chart? How do we convert things? We like to do this when we're doing conversions. We always want to look at what we want versus what we have. And we need to pay attention to where our want is. Is our want in the denominator? Then we would flip it, what we have over what we want. We always put the want where we want it to go. So start with what you know, always. Doesn't matter what you're doing, start with what you know. I know I have 5,500 millimeters, and it's asking me to convert this into kilometers. What I want versus what I have. I have millimeters. What's the next common piece of information that we deal with? Remember, our base unit is meters. Let's go meters. So here I'm at 10. I need to get to the 0, 10, 100, 1,000. So in 1 meter, there's 1,000 millimeters. Am I in meters yet? Or am I in kilometers yet? No. Okay, I need to do one more conversion. I want kilometers, I have meters. And so in 1 kilometer, kilo meaning 1,000, I have 1,000 meters. And so in my calculator, I'm just going to go 5,500 divided by 1,000 divided by 1,000. I could go 5,500 times 1 for 5,500 divided by 1,000, which would be 5.5. And then I could go times 1, which would be 5.5, and then divide it by 1,000, and I would get 0.0055 kilometers. I could do that. Or I could just divide by 1,000, because anything multiplied by 1 is itself, and anything divided by 1 is itself. The other thing that we need to pay attention to is how many significant digits are there here. There's 1, 2, 3, 4. Over here, I currently only have 2. So my answer actually needs to be 0.005500 kilometers. The other one that's really quite common is to go between kilometers per hour. Quite often, boats and vehicles travel at kilometers per hour, not at meters per second, simply because that's what the speedometer is telling us. It's calibrated in kilometers per hour. And so we're going to start with what we know. And we're going to, our target is meters per second. That's what our target is. So let's pick one unit to convert first. Let's convert kilometers. So what I want over what I have kilometers, I want meters. That's what it says, I want meters. And I know that when I go back to this lovely chart, that when I'm here at the base unit, and I want to go to kilo, it's 10, 100, 1,000. There's 1,000 meters in 1 kilometer. And then I can look and see that a kilometer divided by a kilometer cancels out. And I have my meter in my numerator. But I'm not done yet, because in hours, I want to get to seconds. And so because time is in the denominator, my want is going to be down in the denominator. What I have is an hour. Now, can we go from an hour to seconds? Absolutely. Are we familiar with that process? Not really. So the most common that we're familiar with is hours to minutes. In 1 hour, there is 60 minutes. And my hours cancel out, but I'm in minutes, I'm not in seconds, so I have to do one more conversion. What I want versus what I have. I want seconds, I have minutes. And in 1 minute, there are 60 seconds. And so then I am now finally left with meters per second. And so I'm going to go 20 times 1,000 divided by 60 divided by 60. And I get 5.555. Repeating. When I go back to the original question, there are 2 significant digits. Therefore, my answer can only have 2 significant digits. This 5 will have an influence on that one. My answer is 5.6 meters per second. Let's try it again. We have 720,000 seconds, and I want to end up in years. Start with what you know and take all the steps to get there. I want, right? This is in the numerator. I want versus what I have. I have seconds. The next common one is minutes. In 1 minute, there are 60 seconds. Again, I want is in the numerator, what I have. I'm now in minutes. So minutes, the next common jump is hours. In 1 hour, there are 60 minutes. The next jump, hours to days. In 1 day, there's 24 hours. And then the last jump, days to years. There's 365 days in 1 year. And we're not going to get so technical that we're going to go 365.25. We're not going to worry about the quarter of a year. That is typically there. We're just going to go with the 365. And we can follow our cancellations through minutes, hours, days, and we're left with a year in the numerator position. So we've set everything up correctly. Whether we've used the right numbers or not, that's debatable, but we've set everything up correctly because we ended up with years in the numerator. So 720,123 divided by 60 divided by 60 divided by 24 divided by 365. And I get 0.002283. How many significant digits are there? 1, 2, 3, 4, 5, 6, 4, 5. Well, I'll just write it out over here. 0.002283,105. So we need 6. 1, 2, 3, 4, 5, 6. 5 will have an influence on this 0, and these guys here are leading zeros. They don't count. So our answer is going to be 0.00228311 years. Okay? So now you're going to pause. You're going to go through page 6, 2B, C, E, F, H, J, and 4A, C, D. And then you're going to try the review assignment that's posted on Google Classroom. You can only go as far as the end of question 6 because question number 7 is a graphing question, and we're not there yet.